So with these problems in 7.4 and trig substitutions, you have to follow a certain technique. And what I'm going to do is kind of take you through the techniques. These are integration problems that can take a lot of work. So one of the things I want to kind of show you on here to begin with is we're going to look at integrals, and somewhere in the integral you have something that looks like this. X squared plus a squared. A is a constant. A squared minus x squared minus a squared. That's what we're focusing on. So like if you look at this first example we're going to do, you have a 1 plus x squared in it. It has a structure. If you look at the next page, okay, you got something minus x squared and so forth. So we're going to kind of look through integrals of that type. They may have a radical in that. They may have a power. But the idea is always going to be the same. Every problem I'm going to do is either going to have x squared plus a squared, x squared minus a squared, or a squared minus x squared. There's three situations. Now, one of the things I'm going to kind of show you is, and you don't need to go this page because I just want to show this to you, but on page 6, there's kind of a summary of the setup of the three different situations we're going to deal with. So we're going to use what we call trig substitutions. There's going to be a case when you have a squared minus x squared, you use what we call a sine substitution. If you have a squared plus x squared, that's a tangent substitution. Then if it's x squared minus a squared, it's a secant substitution. So we're going to look at sine, tangent, and secant substitutions. The reason these work is because of the way identities work. So you also have to know something about your trig identities to do this. So I'm going to go ahead and start off with this problem. And a couple of things that you want to be really solid on, again, is these three identities. You can write them down if you want to, but you don't have to. I'm just kind of reminding you that those are going to be a real big deal in the different trig substitution problems you're going to do. So the first thing that you do with these things is you look at a triangle in a certain way. Now this one has a structure of a squared plus x squared in it. So that is going to be focusing on this triangle right here. So what I want to kind of do at the beginning of this is we're going to set up a triangle kind of like this then. So we're going to let theta be that base angle right there. And it's going to go like this then. So what you're going to have with this is when you're doing a sine, you're thinking about opposite over hypotenuse. So what we're going to do is we're going to set up x there. Now a is what you square that would give you that. So really what you have is 1 squared plus x squared. So that's going to end up being a 1 like that. All right. And what we're going to do on this is we're going to do a tangent substitution. And then from the Pythagorean Theorem, it kind of goes like this. So first of all, the first thing that we would have in this is the tangent of theta. Remember, the tangent of theta is what? Opposite over adjacent. So what would it be equal to in this triangle? That's what we want. We want it to be something kind of simple like that. So we would end up having the tangent of theta is just equal to x in that problem then. Now, the reason we do this, by the way, is because of how the Pythagorean Theorem works, okay? So I'm going to just do this kind of at the side here. You don't necessarily have to write this down, but it's important that you understand this. So like if that was like your c in the Pythagorean Theorem, then we would just have c squared equals 1 squared plus x squared. So that would be c squared equals 1 plus x squared. So what would c be equal to? Square root of 1 plus x squared, and that's what we're trying to integrate. So that's kind of the idea. You want to understand how this triangle works and why it works. So we're going to do what we call a trig substitution on there. So what happens on this is that 1 plus x squared becomes a hypotenuse of a right triangle where x is the side opposite. And then, like if that was a 4 instead of a 1, that would be a 2, right? If that was a 9, what would that be? A 3 and so forth. So you're setting up a triangle and applying the Pythagorean Theorem. All right, so one thing I wanted you to just kind of write down on this then is in this problem, 1 plus x squared can be thought of as the hypotenuse of a right triangle. and the legs are 1 and x. The legs are the two things that make the right angle like that, okay? All right, so now I'm going to show you how we do this substitution on this, and this will have a bunch of steps on it, so watch carefully. So first thing I'm going to do is with the triangle, I'm going to write my substitutions. I have x is equal to the tangent of theta, like that. We're changing the variable too. And then dx is going to be secant squared theta times d theta, like that. Okay, so we're going to have that. Now we're going to do a substitution in this integral. Okay, so watch carefully. Okay, what we are doing is we are integrating the square root of 1 plus x squared times dx. So we're going to plug in everything that we know. Okay, so the first thing is x is equal to the tangent of theta. So you're going to replace that x with tangent of theta. Okay, the next thing we have is dx is equal to this. So we're going to plug that in, and then we're going to see what kind of integral we have. Okay, so when I do that, I'll go ahead and set the integral up. I'll have the integral of square root of 1 plus tangent squared theta, like that. And then I'll have the dx is just going to be secant squared theta d theta, like that. Let me erase this stuff over here because I've got that written down anyway. Okay, and then we'll kind of pause there, and I'll see if you got any questions about the setup. The y part will come here in a minute, why we're doing that. Okay, so that's how we get that thing set up. Now we've changed the variable. Whenever you do this integral, your answer's got to have x's in it. So at the very end of the problem, you want to make sure that you transition that theta back to an x, like that. All right, do you guys follow the substitution? Okay. All right, okay. Now, let's think about why this might be a good approach to doing this integral. First of all, if you look at this thing right here, we have an identity that will make that very helpful, right? Okay, so if you look at your trig identities, we know that 1 plus tangent is the secant, right? Okay, so we transformed this sort of into a situation where you can apply one of these identities. So the next thing I'm going to do is I'm going to replace this thing with the secant. So I'm going to end up with the square root of the secant squared of theta times secant squared of theta times d theta, like that. Okay, and then we're going to just kind of see what kind of integral we have. So everything okay so far? Okay, now the key is you got to set that triangle up. You know, as you're learning this, just refer to this diagram right here. That will tell you that you have to set up a tangent triangle on that. Okay, so what I'm going to have from here is the square root of something squared is itself, so that's going to be the integral of secant theta times secant squared theta times d theta, like that then. Okay, so now what we got to do is we got to think about how in the world we're going to do this integral right here. So let's see, if we think about this a little bit, one of the things that I see on this a little bit is we might want to break this up a little bit. We may end up having to do like an integration by parts on this thing too. So I'm just going to kind of pause at that point, and you could write that certainly as secant cubed of theta if you wanted to. Okay, well, let's see. If we did parts on this, because this one is kind of, if you did a U substitution, it'd be kind of challenging. If you changed the secant back to a tangent, I think you would be off a little bit on that too, so I don't think you'd probably get anywhere that way. So what we're going to do is go ahead and focus for a minute on this integral, and we're going to do this with a integration by parts technique, okay? And again, when you're doing an integral, if U substitution fails, then parts is usually a good next strategy. So what I'm going to do with this one is do our integration by parts. So I'm going to write down this integral, and let's see if we can figure out how we might want to take this into integration by parts. Okay, so let's get this set up. So remember, on integration by parts, we have to figure out u dv to start with and figure that out. Okay, so let's think about this a little bit. Okay, when you're doing integration by parts, okay, you want dv to be something that's easy to integrate. So is there anything in there that's easy to integrate? Secant squared is easy to integrate. What's the integral of secant squared? Tangent. Okay? We want u to be something that's pretty easy to differentiate. Can you differentiate secant? Yeah, that's secant tangent. Okay, you may not remember that, but that's what that is. Okay, so let's try that approach and see where it leads us. Okay, I'm not sure where it'll lead us, but I have a kind of an idea. So let's see, let's let that be the secant of theta, and then let's let that be secant squared theta like that. Okay? All right, so du is the derivative of a secant is a secant tangent, and that'd be d theta, and then v is going to be tangent of theta like that. All right, so let's see what kind of integral we have in integration by parts now. So remember, the integration by parts formula is you have u times v minus the integral of v du. Okay, so let's put that in and let's see what we are encountering here. Okay, so let's see if we do u times v is those two things. Okay, so if we do that, we're going to have secant theta times tangent theta like that. And then we're going to do the integral of v du. Okay, so integral of v du is going to be these two things together. Okay, so that looks like that is going to be secant theta tangent squared theta times d theta like that. Okay, so let's see what we got here. Okay, we got secant theta tangent theta. That's not a part of an integral. So now what we got to do is we got to think a little bit about how we might approach this integral right here, and kind of thinking about this a little bit as we do this. Now I think this one ends up being, if you look at this integral right here, u substitution doesn't work on this one. And just think about why this is. So if you let u be secant, well, the derivative of secant is not going to help you. If we let u be tangent, the derivative of tangent secant squared, so that isn't going to help you. So one of the things that you might think about is, well, the only identity you could use is that tangent squared identity. That would get you back to a secant cubed, so that's no good. So remember what happens on integration by parts every now and then. You have to do it twice. Okay, so that may be what we have to do here. Okay, that's what I'm thinking anyway. All right, so let's see what we got here. So let's go through. Now, when you do integration by parts twice, first of all, one of the key things when you do that is, I'm going to go ahead and just write this. The integral that we're really doing is, what we're really doing is the integral of secant cubed theta d theta. So far what we have is secant theta, tangent theta, and then that right there should be a minus. Then we have minus the integral of secant theta, tangent squared theta, d theta like that. So I'm thinking that we got to go through and we got to do this one more time here with integration by parts. Okay? So let's see. If I go through and do this now, this is what I'm seeing on this. Okay? So I'm going to keep writing this down. This thing right here, I can use this identity that I know. Okay? We know that we have the identity that 1 plus secant squared theta is equal to tangent squared theta. Okay, so what I'm going to do on this one is I'm just going to replace that in there. Did I do that backwards again? That's no, I keep doing that backwards. I just can't remember that identity for some reason. So it goes like that. Okay, I've done that 3 times today too, and I still can't remember it. Okay, so what I'm going to do is I'm going to move this 1 over here, so I get tangent squared theta is equal to secant squared theta minus 1. Now there's a reason why I'm doing this. So what I'm going to do is I'm going to replace that tangent with this, and what I'm thinking is I'm going to end up with a secant cubed in there again. So I'm going to bring this down, write that as secant cubed theta d theta, and then this is secant theta tangent theta minus the integral of secant theta. And then I'm going to replace this with secant squared theta minus 1 d theta. Now the reason I'm doing that is because, see, if you look at this integral right here, you have a secant cubed. And you like it when the integral turns out to shows up again that matches the original when you do integration by parts twice. So you got to keep writing steps very carefully on this. Okay, so let's see what we have here. I'm going to keep writing down this left side because it's important that you do that so that you see this the right way. So you just keep rewriting this stuff. That's okay. Don't be lazy about it. Just do it. Okay, I'm going to multiply this out. That's going to give secant cubed theta minus secant theta d theta like that. Okay, so what we have then is, if you look at this, I've got a secant cubed theta right there, and I can split this thing off here into two integrals, and then I'll kind of see where that leads us. Okay, so I think I'm figuring out kind of where we need to go. So I'm going to write this as secant cubed theta d theta. Just kind of bring everything down. So I got secant theta tangent theta. And then I've got minus the integral of secant cubed theta d theta. And then I got a minus minus, so be careful about that. So that's a plus integral of secant theta d theta like that. Okay, so we're getting pretty close to doing this now. Now the other thing that you got to know, if in the previous section we kind of had a formula for the integral of the secant. That's ln of secant theta plus tangent theta. What's that?
Like secant, there's
minus secant theta.
The very last one.
What about it?
It should be a minus secant.
It's minus a minus.
It's minus a minus. Okay, because what you're doing on that is you've got that whole grouping right there, right? Okay, you guys see what I'm doing?
Yep.
Okay, because what I'm doing is I'm breaking it up into two integrals. So you have minus the integral of negative secant. So that's a plus. Okay? Okay, you see what I mean? Okay. So here's what happens on this. So we're kind of getting close here. Now this thing right here, this is something that I put in your notes for the last section, is the integral of the secant is that. If you don't know that, you can look that formula up. That'll show up every now and then. So what I'm going to do now is this. All right, now see how this is what's real key on these problems, is see how those are the same? So what do I need to do? I'm trying to find the integral of the secant cubed theta. What do I need to do with that secant cubed on the right? I need to move it, okay, because I got to solve an integral equation. So what I'm going to do is we're going to move this thing to the right. Okay, now watch carefully how I write this now. So we're going to have secant cubed theta d theta plus, I'll see that minus moves over, so that's plus secant cubed theta d theta. Okay, that's equal to secant theta tangent theta. And then this thing, we're just going to look up that formula. So that's going to be ln secant theta plus tangent theta like that. Okay, so we got that. All right, everybody following me okay? Okay. Don't forget, sometimes when you do integration by parts, you have to do it twice. It's just what you have to deal with every now and then. Okay, so these are like terms, right? So that would mean that you have 2 secant cubed theta d theta, and then this would be equal to secant theta. I'm just going to rewrite all this out. Okay, like this. And then we're getting close. Okay, we're not done though. I mean, we still got one more thing to do. All right, what do I need to do now? Divide by 2, right. Okay, see, this is what we want, is we were trying to integrate this. So we don't want that 2 there, so you can just multiply both sides by a half and make sure you do that whole entire side like that. Then you finally got your plus c. So what we end up having for now is we have integral of secant cubed theta d theta. Now what I'm going to do is go ahead and just multiply the half through there. So I'd have 1/2 secant theta tangent theta plus 1/2 ln secant theta plus tangent theta like that. plus c. Okay, so I got that. That's a big problem right there. Now I'm not done. Okay, we've done a lot of work on this already, but one of the things you've got to be careful about when you do this, now we've done the big hard part of the problem, is remember what we were trying to find ultimately was the variables were x, right? Because the original problem, if you go way back up, was the integral of what? Was it 1 plus x squared? Okay, we don't want theta there. Now the last thing we do is actually very easy. We just get our triangle out and we get everything put back together. So watch this last step. So what I'm going to do on this is I'm going to go through it at the side just so you can see this okay, is the right triangle that we drew on this problem was like this. We had theta, we had x, we had 1, and we had 1 plus x squared. Okay, so what you got to do at the end of the problem is you want your answer to be in terms of x. Okay, so we're just going to do the secant, tangent, and then put it all together. Okay, so you got to know these definitions from trig. A secant of theta is hypotenuse over adjacent. The tangent of theta is opposite over adjacent. So what I'm going to do is I'm just going to put that all back together now. So watch carefully and tell me if you remember this from trig. So a secant would be what? It would be hypotenuse over adjacent, right? So that would be square root of 1 plus x squared over 1. I'm going to put the 1 there to just emphasize that. Okay? What's the tangent in this triangle? What's the tangent?
X.
Opposite over adjacent, right? So that's x over 1. You guys remember that from trig? Okay? SOHCAHTOA stuff? All right? All right, so we got that. So that'll take care of that. We'll simplify that in a minute. Then over here, you're going to have 1/2 ln. Again, the secant is hypotenuse over adjacent. So that's going to be square root of 1 plus x squared over 1. And then the tangent is opposite over adjacent, so that's x over 1 plus c. Now all I need to do is just kind of clean this thing up, and then we'll see if we got a good answer here. Okay? So the final answer I'm just going to write like this. I'm going to write that as 1/2 x root 1 plus x squared. Okay, then over here I'm going to have 1/2 ln, absolute value, 1 plus x squared plus x plus c. That's it. Okay, that's a pretty hard problem. It's got a lot of stuff going on in it, but this is what we call a tangent substitution. And the key thing on that is getting it set up. And then this one just happened to be an integration by parts twice. You just got to deal with it when it shows up. Okay? All right, does that make sense? You guys follow the logic?
So, can you just go over one more time?
Sure.
How you went from here to here?
From where to where?
From this step to that step.
First step.
I did integration by parts. Okay, so what I was doing there was u times v. Okay, so I've got u times v is secant tangent. So that's where that is. Okay, then I'm doing minus v du, so that's secant tangent squared.
Right, and then to the
And then
next.
from here, what I did is I just brought that down. This thing right here, I just brought this down too.
Okay.
Now all I did is, what we were doing ultimately was we were ultimately doing the integral of the secant cubed theta. That's what we're trying to solve. So I went ahead and just wrote that down. Because if you have to do integration by parts twice, it's important to keep track of that integral. Like that.
Okay.
I'll say, and then from there, basically, I used an identity there.
Right, yeah.
Okay, right there. So that just came from integration by parts.
Okay.
But I wrote that, and what I did is I wrote that left side down because I was beginning to see that that integration by parts twice is what you'd have to do. Okay, so what do you think? Yeah.
I still don't believe that this would be positive, because
You still disagree with me.
we're not integrating this integral. This integral negative.
Let me
this
show you.
integral minus this integral. How did this negative become positive?
That's fine. Let me prove it to you. Okay. Okay, if you're looking at, okay, what you're looking at is minus the integral of secant cubed theta minus secant theta, right? I didn't show the step, but this is technically what you're doing. Okay, what I'm doing is I'm breaking this up into the integral of the secant cubed theta minus the integral of secant theta, like that. Now, what happens to the negative? It distributes through, right? So it's negative secant squared theta, which I have, or secant cubed theta, and then you have the minus is plus.
Okay.
Okay? Are you convinced now?
Yes.
Okay, that's fine. Okay. You got to be really careful about little issues like that, because that would have thrown off the answer, obviously. And I did that in my head, so I'm just kind of thinking of a grouping, breaking the integral into two parts. That's the idea.
Witchcraft is a real thing here. So.
What's that?
Witchcraft is a real thing here. So
yeah.
Sometimes when you don't believe it, just say witchcraft and keep moving on.
You can do that if you want to, too. I can just say, trust me, okay?
Yeah.
Okay. All right, so
yeah, pretty much.
so this next one, and we're going to do another, this one's a different substitution. So we're going to kind of look at this. So again, look at the structure. So when you're doing your homework, you know, one of the things that you want to do as you're learning this is, you know, refer to this page on your notes. This is page 6. You don't need to turn there. But this tells you the triangles for the different situations. So that's the key. What we're getting ready to do now is a sine, because we have a structure a squared minus x squared. So this second example, we're going to look at a sine triangle. So I went ahead and just pulled up the triangle so we can refer to that as we run through this now. So the key thing on this is, first of all, just kind of rewrite this expression like this. This is really a 5 to the second minus x to the second. Okay, and then when we do this, we're going to put the theta there, and we're just going to follow this diagram. Okay, so what we're going to do is put the x there, and then we're going to put the a here. Now a is 5. That's what's being squared, so that's going to go there. And then this is going to be 5 squared minus x squared, like that. Now, let me show you where this comes from. And I'll kind of begin, as I'm doing this, I'll show you how I remember some of this stuff too. So in the Pythagorean Theorem, let me just prove to you that this is right. So if you do x squared plus square root of 5 squared minus x squared squared, that should be equal to 5 squared. I'm just doing a squared plus b squared equals c squared. So let's see if that's right. That's x squared plus 5 squared minus x squared equals 5 squared. Is that right? It is. Okay, so see, all I'm doing is these ratios right here, ax and a squared minus x squared, those are coming from the Pythagorean Theorem. So that's how you set that up. Just follow that diagram as you're doing this. So what you're going to kind of look at here on this one then is, it kind of goes like this. So what you have when you look at this expression, the hypotenuse is 5, the other leg is x. Okay, so that's a leg, and then that's right there. So what we're going to do is we're going to do a sine substitutions. Okay, so let's start our substitution, because that's the whole key. The whole key to these problems to me is drawing that triangle correctly and then getting your trig substitution done. Okay, so let's look at what the sine of theta is. So what's the sine of theta in this triangle? Opposite over hypotenuse, so what is it? Okay, and see, that's what you always want, guys, is you always want trig function equals x over something. Okay, you don't want the square root or anything to be in that trig substitution. So then what we can do is we can solve this equation for x. So we can multiply both sides by 5, so that's going to give x equals 5 sine theta. That's what the rule is they have there. I don't do it that way. I just find the sine and solve for x. That's my strategy. Now what we're going to do is dx. So what's dx? Cosine, right? Okay, that's going to be 5 cosine theta d theta, like that. Now we're ready to do our trig substitution. Okay? All right. Okay, I got somebody just staring at me too. Okay, go away. Okay. Somebody's just sitting there staring in this classroom. I was gazing out in the window there. So then I started making eye contact with him. He fled. Okay. So, okay. Okay. All right. So let's go ahead and let's get this put together. Now let's just not worry about the limits of integration right here. Let's do dx over square root of 25 minus x squared, like that. So what we're going to do is we're going to carefully do the substitutions. X gets replaced with 5 sine theta, and dx gets replaced with 5 cosine theta d theta, like that. Okay? And I'm not going to worry about the limits of integration for now. I'm just going to kind of pause, just leave that alone for now. Okay, so when we do that, we're going to have dx is going to be 5 cosine theta d theta. Okay, the denominator is going to be square root of 25 minus, and then in parentheses, 5 cosine theta squared d theta. You can skip a few steps if you can do a few things in your head. Okay?
5 sine theta.
Oh, I put that, yeah, thank you. Okay. Yeah, d theta, or no, x dx was 5 cosine theta, but x is sine theta, like that. All right, be careful how you get everything substituted in. So let me make sure. I think I'm good. Yeah, okay, so everything's good now. Okay? Now, here's the reason this works. Once you start practicing these problems, you'll begin to see why this works. So I'm going to have 5 cosine theta d theta. And I put an extra d theta in there too. So I got d theta d theta. Okay, that's not good. Okay, so what I'm going to have in the bottom, I'm going to have square root of 25, and then you square this thing out, so that's going to give 25 sine squared theta. Okay, like that. Okay, so I've got my substitution put together there now. Okay, does everybody follow that okay?
Yeah.
Okay, now here's the deal. Here's what happens and why this works good. If you look at the denominator, first of all, that's a perfect square. Okay, and if you factor the 25 out, you'll end up having 1 minus sine squared. Now, what is 1 minus sine squared? It's cosine squared. What's the square root of cosine squared? It's cosine. That's what's happening. If you have that radical in there, that's kind of forcing that to come out of the radical. That's what that trig substitution is ultimately doing. So what we're going to do as our next step is we're going to factor. Okay, so we have the integral of 5 cosine theta d theta. Okay, well, you want to factor out the 25. I'm just going to try to write every little step on here. So that's going to be 1 minus sine squared theta, like that. Okay, and again, you almost always on these problems use one of the Pythagorean identities. So this thing right here we know is a cosine squared. All right, so I'll move it over here, and we're going to have now integral of 5 cosine theta d theta. And then that's going to be all over the square root of 25 cosine squared theta, like that. All right, you guys follow me okay? Okay, so now what we have is we have the integral of 5 cosine theta d theta all over 5 cosine theta. Wow, I love this one. This one's working out beautifully. Okay, so let's see kind of where we're at with this then. So those are going to cancel out. So we're going to end up with about as easy of an integral as you can possibly do, is the integral of d theta, like that. Okay? All right. Everybody good so far? Okay, so what's the integral of d theta? Theta. Okay, like that. And I'll put the plus c. Now we are going to go back and we're going to do the limits of integration when we do this now. Okay, so we got that. We've got the integral done. But the key thing on this one now is you got to go back to your triangle. We don't want theta in the answer. Okay, and I'm going to go ahead and take that back to x, and then I'm going to do the definite integral like that. So what I'm going to do is kind of draw this triangle at the side again, just so you can see this. You don't have to write this down because you've already got it. So I just want to show you kind of what the connection on this is then. Okay, so if you go back and if you look at theta in this problem, and if you also look at this substitution, the original substitution we had was 5 sine theta. So we got to write theta back in terms of x. So if you look at the fact that we have x equals 5 sine theta, I need to solve that equation for theta. Okay, so what I'm going to do is I'm going to divide by 5. So I'm going to have x over 5 is equal to sine theta like this. Okay, now I need to solve that for theta. This is a trig background thing right here. Okay, you could tell me, if you remember your trig, you could tell me what theta is. Can you? Good, inverse sine. Okay, or you can do it this way. Okay, if you take the inverse of both sides, the inverse sine of both sides, that's one way to look at this. Then what you would end up having is you would have inverse sine of x over 5 equals theta, right? So that's what you have. So this thing right here becomes inverse sine of x over 5. Now we're not going to do the plus c. We're going to go back now. Since we're doing a definite integral, we were asked to do this from 0 to 5 over 2 anyway, like that. Okay, so an inverse sine shows up in this problem. Okay. All right, does that make sense? Okay, so now we need to evaluate the integral and then we'll be done. The integral worked out beautifully on that one. Sometimes they're easy. Sometimes they take a lot of work. So when we do this, it's more trig background issues that you need to kind of make sure you're good on. Okay, so when we do the definite integral, it looks like we're going to have inverse sine of 5 halves over 5 minus inverse sine of 0. Okay, like that. Okay, well, let's see. The 5s are going to cross out. I mean, you're really just doing 5 halves divided by 5. So that's 5 halves times a fifth, so that's a half. So whoever made this problem up, the author of our book, I guess, that's where I took it, designed it so you could go to the unit circle. Okay, so we got that, and then we've got inverse sine 0 like that. Now all we got to do from here really is just kind of look at the unit circle on that. Okay, so on a unit circle, the place where the sine is equal to 1/2 is at the place where it's the lowest. You'd have the point square root of 3 over 2 1/2. That's really 30 degrees. Okay, that's 30 degrees, but we don't do degrees, we do radians. So what's 30 degrees in radians? Pi over 6. So that's pi over 6 is what that is, okay? And then what we'd have here, if you're looking at the inverse sine of 0 at 0 radians, you have 1, 0. Okay, so the inverse sine of 0 is 0. So that means the answer to this problem is pi over 6. Pi over 6 minus 0 gives you pi over 6. Okay, so when you get down to doing inverses, you got to go back to your unit circle. The other thing that you might want to make a note of, if you need to, is the range of an inverse sine. Do you guys remember what that is? It's from negative pi over 2 to pi over 2, including the endpoints. So if you're asked to do an inverse sine, you got to make sure your answer falls within that range. And there's only one answer to it like there. So see, there's your trig background stuff. Now that you're in Calc 2, you're beginning to see everything hopefully coming together, right? Trig, algebra, everything that you've learned in the past starts coming together and crystallizing, right? That's why I like Calc 2 so much. It all comes together. Yeah.
So for the first step, you're trying to isolate your x and then get rid of and like put the radical like to the side for later. Is that the point of the first step?
Yeah, the substitution is you're actually are simple when you put that expression under the radical, then a lot of times what happens is it comes out of the radical. Okay.
Like with the setting up the triangle, you're trying to get something you can substitute for x.
Right.
To solve it. Okay.
Right. You're turning it into a trigonometric integral that you can deal with. And the way that I always look at this is you're always going to have, like the last problem, if you look at the last problem, the substitution we had was tangent is x over 1. We always want to have x over something in our substitution. Okay, so notice here we just had x equals, a tangent of theta is x. In this one that we just did, what we have is sine of theta is x over 5.
So you always just want to get x equals.
Right, exactly. So you set the triangle for that reason, okay? Now, when you're doing your homework, as you learn this, look at the situation and look at the triangle. And then eventually you'll get the idea that the reason I do a sine on this problem is because I want x over something. The reason I use a tangent on the other example is I wanted x over something. I don't want that radical in the substitution, and I think that's what you're alluding to.
Yeah, exactly.
When you said we kind of save it for later. Yes.
I'm trying to wrap my head around why we
Yes.
the triangle.
Yeah, you end up working with the radical, but the radical is not a part of the substitution. Okay, all right. Okay, very good. Okay, so let's run through this next example here and see kind of what we have on this one. This is another sine substitution. So the first thing you want to kind of look at is you want to know what you have. And I'm doing lots of different situations. This one has a variable x in the bottom, but it's still the same idea. It's a squared minus x squared, so you're going to set your triangle up like this. Okay, first of all, tell me what a is in this problem.
3.
Okay, that's important. Okay, that's 3 squared minus x squared. You're generally going to be working with integrals with perfect squares in them. Okay, those numbers are going to be perfect squares. So on a sine substitution, that's your theta. Then you want to put your x there. You want to put your a there. And then this would just end up being the square root of 9 minus x squared. And again, that's Pythagorean Theorem. That's how that goes. Now, one thing that helps me a little bit, because you start having to have, how in the world do I remember all this stuff? Well, if you have a minus, that means that that's going to be a leg of the triangle. If that's a plus, that's a hypotenuse. That's how I remember it. Because a squared plus b squared equals c squared, that would end up being plus. Okay? But if it's minus, it's got to go with a leg. Okay? That's how I remember it. Okay? That might help you a little bit. For now, you can look it up. Okay, so what we're going to do now is we're ready to do our substitution. So what we're going to do is the sine substitution. So we say sine theta is opposite over hypotenuse, so that's x over 3. In your head, you can multiply both sides by 3 to get x equals 3 sine theta. Okay, so that's our substitution. And then dx, you want to do that too. That's going to be 3 cosine theta d theta like that. Okay, then we're ready to get everything substituted, and then we'll kind of focus on the integral. Okay, so we're going to integrate 9 minus x squared over x, okay, times dx. Okay, and see kind of where we go with it. Okay, so let's see. What we're going to plug in, everywhere we see an x, we're going to plug in 3 sine theta. Where we see dx, we're going to plug in 3 cosine theta d theta like that. Okay, so let me just kind of go down the list, get it set up, then we'll kind of talk about what kind of integral we're putting together here. So this is going to be 9 minus, and then you're going to have 3 sine theta squared, like that, and then the denominator is going to be just 3 sine theta, and then the dx is going to be 3 cosine theta d theta like that then. Okay, so that would be kind of the idea. That's the substitution part. And then we need to kind of clean it up and see what kind of things cancel and stuff like that. Generally, you're going to have some things that simplify. So I'm going to write this as 9 minus 9 sine squared theta, just squaring out the 3 sine theta, over 3 sine theta times 3 cosine theta d theta like that. Okay? Now, let's see. Well, one thing obviously that happens is the 3's cross out. If you see something cross it out, by all means cross it out. Now, as you start doing these examples, you'll begin to see what happens on these problems. And it happens over and over again. Look at this radical. What's going to happen? You're going to factor a 9 out, right? The 9's going to come out of the radical. You're going to end up with 1 minus sine squared. But what is 1 minus sine squared? Cosine squared. And the cosine squared comes out of the radical. You see what I mean? Okay, that's the reason that the design of this trig substitution works so well. Okay, so that's what you have to kind of do here. So I'm going to write this as factor the 9 out, and you can skip a few steps if you're doing this. I'm not teaching this. I'm going to try to write everything out. So that's 1 minus sine squared theta there. Okay, and then this would be, that's now a sine theta. and that's a cosine theta d theta like that. So again, work with your identity on that. Change that to a cosine. Okay, so that will leave me with the integral of square root of 9 cosine squared theta over sine theta and then cosine theta d theta like that. Okay, you guys follow me okay? Okay. Well, let's see kind of where this leads us now. So now I've got integral of 3 cosine theta over sine theta times cosine theta d theta like that. Okay, so we don't have any radical. That's what happens. Okay, that's why the trig substitution works so good. Okay, so what I'm going to do from here is I'm going to bring this out, and that's going to be 3 times the integral. We can multiply the cosines to get cosine squared theta sine theta times d theta like that. So all the first part of this problem is using the trig substitution. Now you've got to figure out what you're going to do with the integral. Okay? U substitution does not work on this one, because if you think about this, you got to think of it this way. Your only choices would be let u be sine theta. Well, du would be cosine theta, not cosine squared, so forget that. If you let u be cosine theta, well, the derivative of cosine is negative sine, but it can't be in the bottom. Okay, so u substitution doesn't do any good there. So you get to do some things. You could try parts. You could also try an identity there, which is what I'm thinking, is let's just change that cosine to 1 minus sine squared theta. Let's see what happens. Okay, I think it'll work okay. I'm not sure though, but that's what my thought is as far as trying this. So let's go ahead and take that approach next. Let's write this as 3 times the integral. Again, pull out your Pythagorean identity. So you want to write this as 1 minus sine squared theta over sine theta times d theta like that. So I'm going to move this kind of to the side here so I can take up the room that I need to. Okay, so let me move this up here. Okay, so now what I'm going to do is let's split it up into 2 parts. So let's just say 1 over sine theta minus sine squared theta over sine theta times d theta like that. Let's see kind of where that's leading us now. Okay, so now I'm going to write this as 3. Let's go ahead and change this to a cosecant. In the previous section, I gave you a formula. I went ahead and just wrote it down. So this is cosecant theta, and then sine squared over sine is sine theta d theta. So I think we can integrate that okay. Okay, the cosecant, we can use this formula, and we know how to do the integral of the sine. Okay, so you guys follow me okay so far? Okay, all right, so let's write the 3 down, and let's apply this formula. So the integral of the cosecant, you can just replace it with that. Okay, so that's going to be equal to negative ln cosecant x plus cotangent x, like that. And then when we do the integral of the sine, well, the integral of the sine is just the cosine, okay, or the negative cosine. So that would be negative cosine theta, like that, plus c. So that's our integral. Okay, and then I'm going to clean that up a little bit and write this as 3 negative ln cosecant x plus cotangent x, and then I'm going to write this, the minus minus becomes plus cosine theta plus c like that. Okay, so that's kind of what I've got on that so far. Okay, so that's the integral technique on that. You can use that formula, but now I'm not done. Why am I not done? This is important. X. Okay, remember the original integral has x in it, right? You need to go back and change these things. And what did I just do? Look what I did. I just decided to change theta x. That's a terrible idea. So if you happen to write that down, I do that sometimes when I'm teaching. Okay, no.
Yeah, I thought it did work that way.
No, it doesn't work that.
You showed me, I thought the tests and everything that we could do that.
No, it doesn't work. It doesn't work that way. So I've got. I just changed it.
That made it really easy.
Yeah. Okay. So we got theta. Then we got to convert to x like that. So really, this is the easy part of the problem. You just kind of go back and you look at your triangle again. So what I'm going to do is just kind of put this triangle over at the side here, and you don't need to write it down again. I think we had square root of 9 minus x squared, we had x, and we had 3 like that. So what you do now is you just look at that triangle and do the cosine, cotangent, and cosine, and then that puts you back in the form where you just have an x like that. Okay, so this is going to be 3 negative ln. Okay, remember the cosecant is hypotenuse over opposite. So that's going to be 3 over x. So you're going to have a 3 over x there then. Okay, and then the cotangent of theta is adjacent over opposite. So that's going to be adjacent is root 9 minus x squared, opposite's x. So that's going to be square root of 9 minus x squared over x. So that closes that part out right there. And then what we're going to have is we've got to have the cosine. So we're doing the cosine. So cosine of theta is adjacent over hypotenuse. So adjacent is this. Hypotenuse is 3. So that's going to be plus, there we go, square root of 9 minus x squared over 3 plus c, and then I'll clean that up and I'll see if that's the answer I'm supposed to get here. All right, now I'll just leave the negative. Now I'm going to just kind of do this. I'm just going to multiply everything out here. So what I'm going to do is just distribute this. So this will end up being, let's write this as negative 3 ln. This part right here already has a common denominator, so you might as well just put it together in the same fraction. That's what I'm going to do. So that's 3 plus square root of 9 minus x squared over x. And then this thing's out kind of at the side, like this. And let's see, with this, I've got... Okay, so I think hold on here. I think I'm okay. Oh, hold on. There's one little issue I did on here. One issue. You know what I did? Oh, man, you got to be so careful with stuff when you're doing this stuff. So careful. Look at this. Okay, bracket. Look at this. Okay, I kind of lost my bracket. So basically at this stage, right here, you need to have, that comes down, but then you're going to multiply that by 3, so that 3 shouldn't be there. Okay, I lost that bracket when I was writing that down. So we need to make sure we get that corrected, and then we'll have it okay. So basically right here, that's your integral. Now I'm just multiplying everything by 3. I probably could have avoided that by going ahead and distributing the 3 right there. So anyway, distributive properties. You do that, you also do that, and that will cancel out the 3. So that 3 right there should not be there. Okay, and then what I'm going to do is, you can write the answer that way. I'm just going to write the final answer as 9 minus x squared minus 3 ln of this expression. You don't have to do that, but that's just maybe a little cleaner way to write that as like that then. Okay? Okay, that'll work. Okay, now what we've done here so far is we've kind of looked at the tangent substitution and the sine substitution. They're all kind of done the same way. So when you're learning this, look at the triangle diagrams that I gave you in your notes, and that'll help you with that. So that would leave us with, we also have to learn the secant substitution, and we'll work on that a little bit next time. So what do you think so far? We did some heavy-duty integrals today, didn't we? I told you we were going to. Yeah, it's a lot of steps, and you see me when I'm working these out. I mean, sometimes you leave off one little thing, and you got to be very careful when you do that. Okay, so that will wrap us up for today then, and we'll finish this next time.